Welcome, curious minds, to another deep dive. Today, we're pulling back the curtain on something really critical, but maybe a bit unseen, in modern tech. Chip design verification. Specifically, we're talking about FPGA prototyping for ASIC validation. If you've ever wondered how they actually build those incredibly complex system-on-chips, the SoCs that power pretty much everything, well, this is a huge piece of that puzzle.
It really is. And the sheer scale of modern chips, I mean, it's quietly pushed the old ways of testing to a breaking point. You're trying to validate a design, maybe billions of transistors, more lines of code than an operating system.
Wow.
Yeah, pure software simulation just it grinds to a halt. And that leaves companies wide open to really catastrophic flaws.
Flaws that cost serious money, right?
Oh, absolutely. Single design errors can easily cost tens of millions of dollars, months of delay. It's high stakes.
Okay, so our mission today is to unpack why this FPGA prototyping thing has gone from maybe a niche technique to, well, an absolute cornerstone. It's like a crucial bridge for developing these cutting-edge chips. We'll explore its strategic role, how it's actually done, the pretty amazing tools involved, and, where this whole field is heading. You're going to get a shortcut to understanding one of the most vital stages in bringing tomorrow's technology to life. Okay, let's dive in. So, if we start with that escalating complexity, the obvious question is, why can't designers just simulate these things on a computer anymore? What's the fundamental wall they're hitting?
Well, the bottleneck fundamentally is just raw speed. Throughput, pure software-based simulation. It's great, really valuable for early debugging. You get complete visibility inside the chip.
Where you can see everything.
Exactly. But, and this is the huge but, it runs incredibly slowly. We're talking speeds in the hertz range, maybe single-digit kilohertz if you're pushing
sort
it.
of cycles per second.
Yeah. So now imagine trying to boot a modern operating system like Linux or process real-world data streams. In a simulator, that would literally take months, potentially years.
Years. Okay, that's completely unusable for any kind of real product cycle.
It creates this insurmountable barrier for doing comprehensive system validation. You just can't do it.
And the speed limitation you're describing, it completely changes how designers have to approach verification, doesn't it? It means they simply cannot test how the hardware and the software truly work together at speed, or how the chip talks to the real world.
Precisely. That's exactly it. And that's the critical gap FPGA prototyping is designed to bridge by taking the ASIC's design and mapping it onto a physical FPGA platform.
You get hardware speeds, or close to it?
Much, much closer. Verification speeds jump by orders of magnitude. You're looking at tens, maybe hundreds of megahertz.
That's not just incremental. That's huge.
It's a qualitative leap. It means that OS boot goes from months or virtual eons
to minutes. And that unlocks crucial scenarios. Things like long-duration testing, interactive hardware-software debugging. Stuff that's completely impossible in simulation.
Okay, so the why is crystal clear. Simulation just hits a wall. But beyond just fixing the speed problem, what are the really tangible gains? The practical impacts that FPGA prototyping delivers?
Well, there's been a really profound shift in what people see as its main purpose. Historically, it was seen as a hardware verification tool, purely that.
Okay.
But now, its principal value is really recognized as being a critical enabler for software development. Think about it. On modern soft projects, software often eats up 50%, sometimes more, of the total resources and the schedule. It frequently becomes the bottleneck.
So this means the software team gets their hands on working hardware like months before the actual silicon chip is ready? That sounds like a massive time saver.
It is. It's a true game changer for project timelines, this whole shift left idea.
Right. I've heard that term. It lets hardware and software development happen much more in parallel, shrinking the overall time to market significantly.
Yeah.
Software engineers can bring up firmware, develop drivers, port operating systems, even run applications way earlier in the cycle.
And presumably find bugs earlier, too.
Exactly. This early integration is invaluable for uncovering those really subtle hardware-software interface bugs. Things like, interrupt handling issues, weird timing dependencies. These are notoriously hard to find otherwise, often hiding until the very last minute.
Okay, that covers the internal hardware-software integration. What about how the chip talks to the outside world? High-speed stuff like USB or Ethernet.
Right. Yeah, that's the second crucial pillar. At speed, or at least near at speed, validation of real-world interfaces. Simulation can verify the logical correctness, sure, but it just can't replicate the the electrical nuances of real physical connections.
Makes sense.
Prototypes, though, they can connect directly to actual peripherals, real test equipment. This lets you do true interoperability testing. And that's indispensable for finding those sneaky hardware bugs that only show up during live, long-duration operation in a real system context.
And let's not forget the money side. These chips, they're huge financial bets, right? How does prototyping act as, like, an insurance policy?
The financial stakes are just staggering. The NRE, the non-recurring engineering, costs for an ASIC tape-out, easily tens of millions of dollars.
Wow.
And a single design flaw that forces a silicon respin, that's catastrophic. Add 6 months, maybe more, to the schedule, could kill the whole product.
And you said logic errors cause a lot of these.
Functional logic errors cause nearly half of all respins. So FPGA prototyping is absolutely critical insurance against that nightmare scenario. The ROI isn't just about the cost of the prototype system itself. It's the monumental savings from avoiding even one respin. Finding just one critical bug in the prototype phase can justify the entire prototyping effort many, many times over.
That's a powerful justification.
And here's a really interesting strategic shift we're seeing. Prototypes aren't just for internal use anymore. Companies now use them for proof-of-concept demos, showing them to clients, to investors.
So securing design wins or funding before committing all those millions to silicon.
Exactly. It actually transforms the prototype from just a verification tool into a strategic asset that can directly generate revenue or secure funding. Pretty fascinating evolution.
Okay, so it's clearly incredibly powerful. Does that mean FPGA prototyping replaces other verification methods? Or where does it fit in the bigger picture?
No, not at all. It doesn't replace them. It's really a crucial component of what we call the modern hardware-assisted verification continuum. It sits alongside traditional RTL simulation and dedicated hardware emulation.
Okay, continuum. So different tools for different jobs.
Precisely. Each one has its own unique set of trade-offs. Speed, cost, debug visibility. A really robust verification strategy almost always uses all three at different stages of a project. You've got RTL simulation as the foundation. It's software-based, gives you complete visibility into every single signal, lowest cost.
It's slow.
But, as we said, excruciatingly slow. Hertz to kilohertz. So it's great for block-level checks, early design exploration. Then you have hardware emulation. This occupies the middle ground. These are specialized, very expensive systems, think millions of dollars.
Millions, okay.
Yeah, but they offer a significant performance boost over simulation, getting you into the low megahertz range, while still providing really deep debug visibility.
And their weakness.
Their main limitation is usually restricted connectivity to real-world interfaces. It's harder to plug them into the real world. And then there's FPGA prototyping, representing the highest performance tier. Now you're talking tens to hundreds of megahertz, fast enough for real-time software execution, full at-speed interface validation.
And cost-wise compared to emulation.
Generally more cost-effective than those multi-million-dollar emulators.
Yeah.
But traditionally, it came with a more complex bring-up process. And historically, it had more limited debug visibility. That's the challenge, often grimly called FPGA hell. We'll probably get into that later.
Okay, so the ideal flow isn't just picking one tool. It's more like a strategic sequence. Maybe start with simulation for the basics.
Right.
Then move to emulation for really deep hardware bug hunting. And finally, use the prototype for the full system software validation and that crucial real-world interface testing.
It's a very typical workflow, yes. If you want to summarize the trade-offs simply, simulation, excellent debug, very slow speed, low cost. Emulation, excellent debug, medium speed, MHz, very high cost. FPGA prototyping, good and improving. Debug, fast speed, KINS 100s, megahertz, moderate cost.
Got it. Different tools for different phases and problems.
Exactly. They complement each other to cover the whole verification spectrum.
Okay, let's unpack this process a bit more. Taking an ASIC design, something custom built for very specific performance and power targets, and actually getting it to run on a generic, off-the-shelf FPGA. That sounds like more than just hitting compile, right? Must be some serious hurdle.
Oh, it's a very complex undertaking, far more involved than just, recompiling code. The process, often called retargeting, means you have to bridge some really fundamental architectural differences between ASICs and FPGAs. It often gets summarized by these three sort of laws of prototyping. Some sizes are bigger than FPGAs, others are faster than FPGAs, and maybe most critically, SoCIC designs are inherently FPGA hostile.
FPGA hostile, that sounds pretty dramatic. What exactly does that mean in practice for the designers?
It means that ASIC designs often use highly optimized, very specific structures to hit their performance and power goals. Things like custom designed memory blocks or really intricate clocking schemes.
Stuff that doesn't map neatly onto an FPGA.
Exactly. They just don't have a direct, efficient equivalent on a standard FPGA architecture. So overcoming this requires a whole methodology, a holistic approach known as Design for Prototyping, or DFP.
Design for prototyping, okay?
And it's not just a technical checklist. It really has to be a cultural shift within the design organization. Prototyping considerations need to be baked into the main ASIC design flow right from the very beginning. It demands really close collaboration across teams, architecture, design, verification, the prototyping guys themselves.
So you can't just design the ASIC in a silo and then, late in the game, toss it over the wall to the prototyping team and expect it to work easily.
Precisely. Treating prototyping as an afterthought is basically a recipe for major delays, frustration, and potential failure. DFP really succeeds when it's embedded in a culture of concurrent engineering. And a critical part of this, procedurally, is maintaining a single, unified RTL source codebase for both the ASIC and the FPGA prototype.
One code base for both. How did that work with the differences?
You use conditional compilation directives, things like if, diff, and def in the code, to manage those necessary modifications for the FPGA target. This guarantees that the core functionality you're verifying in the prototype is truly identical, bit for bit, to what will be in the final ASIC. That's crucial.
Okay, so what are some of the trickiest specific architectural gaps you have to bridge during this retargeting? You mentioned memory and clocks.
Yeah, memory conversion is definitely a big one. ASICs use these highly customized memory macros designed just for that chip. FPGAs, on the other hand, have standardized memory blocks, usually called block RAMs or BRAMs.
And they don't always match up feature-wise.
Right, you get mismatches. For example, an ASIC memory might allow asynchronous read access, while standard FPGA BRAMs are synchronous. That requires designing custom logic wrappers to bridge the gap. The good news is, modern commercial prototyping platforms now offer automated memory compilers that handle a lot of this heavy lifting, which simplifies things considerably.
Okay, and what about the clocks? You said they were FPGA hostile?
Right, gated clocks are the classic example. In ASIC design, clock gating is a standard technique to fave power. You selectively disable clocks to parts of the chip that aren't active.
Makes sense for power saving.
Absolutely.
Yeah.
But if you try to directly implement that same gating logic in an FPGA, it can be disastrous for timing performance. Why? Because it bypasses the FPGA's dedicated, carefully designed global clock networks.
Ah, so it messes up the timing distribution.
Exactly. The correct DFP approach is to transform that gated clock logic into a simple clock-enabled signal for the flip-flops it controls. The clock itself runs continuously on the global network, but the flip-flops only update when enabled. And again, modern automated tools can usually handle this transformation.
What about high-speed interfaces? Things like SerDes.
Also challenging.
Yeah.
ASIC SerDes, that's serializer, deserializer, and PHY components, are meticulously optimized for extreme speeds, putting the limits of the silicon process. FPGAs have very capable high-speed transceivers built in, but they might not always match the absolute top-end speed of a custom ASIC equivalent.
So you can't always run at full speed.
Not always at the absolute maximum ASIC speed. The common solution is to prototype at a slightly degraded but still high-performance rate. For instance, maybe a 10 gigabit per second Ethernet interface in the ASIC gets prototyped at 2.5 grams or 5 grams on the FPGA. The key goal here isn't necessarily to validate the analog PHY at its absolute max speed, but to thoroughly test the digital logic, the MAC, the controller that sits above the PHY.
That makes sense. You're verifying the digital design's correctness.
Precisely.
And one more, what about really specialized blocks, maybe custom DSPs or accelerators?
Yeah, custom digital signal processors or other specialized hardware blocks in the ASIC often need to be replaced with equivalent functional blocks on the FPGA. This usually means using the FPGA vendor's pre-built DSP slices or other hardened blocks, often instantiated from their libraries. A crucial pitfall to avoid here, though, is using proprietary black box IP from an FPGA vendor that isn't portable, meaning you can't easily synthesize it for the final ASIC.
Ah, so you need to ensure consistency.
Exactly. DFP really requires using synthesizable soft IP cores or developing portable models that accurately represent the ASIC block's function, even if the underlying implementation differs.
Okay, this retargeting sounds complex enough for one FPGA, but you mentioned the first law was that SoCs are bigger than FPGAs. So how do you handle designs that are just too massive to fit onto a single FPGA chip?
Yeah, that's almost always the case for modern large SoCs, and that's where multi-FPGA prototyping platforms become absolutely essential. The ASIC design has to be partitioned intelligently split up across an array of interconnected FPGAs on a board or system.
Partitioning, that sounds non-trivial.
It's far from trivial. It's actually a formidable multidimensional optimization problem. Think about it. Every single signal that needs to cross from one FPGA chip to another introduces a new, potentially long timing path through board traces, connectors, etc.
Which creates timing bottlenecks, right? Slows things down.
Exactly. It can create significant performance bottlenecks. The whole challenge of partitioning revolves around minimizing the number of these inter-FPGA connections, or cuts, and mitigating their timing impact. And the sheer complexity of this problem has really driven an evolution in methodology. Manual partitioning, where engineers would painstakingly divide the design by hand. That was once common, but it's now virtually obsolete for today's multi-million gate designs. It just doesn't scale.
Too complex, too error-prone.
Way too complex, way too slow, yeah. The industry has decisively shifted towards automated partitioning tools. This is a core capability of all the major commercial prototyping platforms now. These tools use really sophisticated algorithms. They try to balance the logic utilization across the FPGAs, minimize the number of I/O pins needed for the connections, and critically, they prioritize timing.
So it's not just about fitting the logic chunks. The tools actively try to avoid messing up the timing.
Precisely. Modern partitioners are timing-driven. They actively try not to cut through critical high-speed paths in the design. They'll prioritize keeping tightly coupled logic, maybe a processor and its local cache, within a single FPGA, even if it means the resource usage across the FPGAs isn't perfectly balanced.
Okay.
They also make a strong effort to keep entire clock domains contained within one device whenever possible, to avoid complex issues with synchronizing signals between different clock boundaries across chips.
But what happens if, even after optimization, you just have too many signals that need to cross between FPGAs, more signals than available physical pins connecting the chips?
Yeah, that's a very common problem. And that's where a technique called time division multiplexing, or TDM, becomes indispensable.
Time division multiplexing, like sharing the wires.
Exactly. It's a technique where multiple logical signals are essentially serialized and transmitted over fewer physical wires, taking turns. The partitioning tool automatically inserts the necessary multiplexer logic on the sending side and demultiplexer logic on the receiving side.
Sounds clever. Is there a downside?
There's a very clear trade-off. Performance. TDM inherently reduces the effective speed of those inter-FPGA connections. The clock running the TDM link has to be slowed down by the multiplexing ratio. If you're multiplexing 8 signals onto one wire, an 8.1 ratio, that link runs 8 times slower.
Ouch, so it's a balancing act.
It's a critical trade-off between achieving the necessary connectivity, just getting the design to fit and connect, and maintaining the overall system performance you need for validation. And one more key practice for multi-FPGA designs. To achieve timing closure, getting the design to meet timing requirements across all those chips, it's highly recommended to register all signals at the partition boundaries.
Meaning add flip-flops on the outputs and inputs between FPGAs?
Exactly. Add flip-flops at the transmitting FPGA output and the receiving FPGA input for every signal crossing the boundary. This effectively breaks up potentially long combinational logic paths that would otherwise stretch across chip boundaries and board traces, making it much easier to meet timing.
But doesn't adding those registers change the design's behavior slightly, timing-wise?
It does introduce a small amount of latency, yes.
Yeah.
Which brings up this interesting point that some people call it the Heisenberg problem of verification. The very act of preparing the system for observation by partitioning it and adding boundary registers fundamentally alters some of its inherent timing characteristics. You're changing the system by trying to measure it. It's a fascinating challenge.
Wow, yeah. Okay, this whole process, retargeting, partitioning, dealing with timing, it sounds like a massive engineering effort. What kind of actual hardware and software platforms make this possible? What does this ecosystem look like?
You're right, it's huge. And success really depends on a sophisticated, multi-layered ecosystem. It starts right down the silicon level, with the foundational FPGA chips provided by the big vendors, and it extends all the way up to these highly integrated, full-stack commercial platforms from the major electronic design automation, the EDA companies.
Okay, so starting at the foundation, who are the key players providing the actual FPGA hardware that powers these prototyping systems?
Well, the market is largely dominated by 2 main players: AMD, who famously acquired Xilinx, and Intel, who acquired Altera some years back.
Right, the 2 giants.
Exactly. AMD's Vertex UltraScale Plus series, especially chips like the VU19P, have been workhorses in this space for a while. Their latest generation, the Versal Premium series, particularly the VP1902, is explicitly marketed as the world's largest adaptive solver, really targeting high-end emulation and prototyping.
What makes it special?
Just massive capacity. We're talking over 18 million logic cells, plus significantly increased I/O and high-speed transceiver bandwidth. It even has a novel architecture with multiple superlogic regions for better routing, and includes hardened ARM processor cores right there on the chip.
And Intel, what's their offering?
Intel's Gradix and Agilex families are also formidable competitors, often built on very advanced manufacturing process technologies. They tend to emphasize high fabric performance, with Stratix 10 claiming speeds up to 1 GHz in some cases. The Agilex family brings some unique features too, like cache-coherent links using protocols like CXL Compute Express Link to connect directly to Intel Xeon processors. This positions them not just as passive prototyping vehicles, but potentially as active, high-performance compute elements in a larger system.
Okay, so that's the raw silicon power, but you mentioned integrated systems. Who provides the complete platforms that pull all this hardware and the necessary software together?
Right, because for large-scale projects, the vast majority of teams use these integrated commercial platforms. It just makes the whole process much more manageable. Synopsys is a major player here with their HAPS platform. HAPS stands for High Performance ASIC Prototyping System. It's used with their protocompiler software, which is well regarded for its automated, timing-driven partitioning capabilities, and it integrates tightly with their VertiDebug environment. Systems like the HAPS 100 can often achieve prototype speeds in the 20 to 50 MHz range for complex SOSIs.
Okay, Synopsys, HAPS. Who else?
Cadence is another giant. They offer the Protium platform. Cadence strategically positions Protium as part of a dynamic duo alongside their Palladium emulation platform.
Ah, connecting prototyping and emulation.
Exactly. They share a unified front-end compiler and debug environment. The idea is to allow teams to seamlessly migrate designs between the high-visibility emulator and the high-speed prototype, speeding up the whole bring-up process. Their latest, the Protium X2, leverages those big AMD VU19P FPGAs we mentioned, aiming for double the capacity and about 1.5x the performance of the previous generation.
Interesting strategy. Any others?
Siemens EDA, formerly Mentor Graphics, offers the Veloce Pro FPGA platform. This one is known for its modular hardware architecture, allowing scalability, and it also has advanced software for partitioning and debug. Their newest Veloce Pro FPGA CS system is based on that huge AMD Versal Premium VP1902 chip. And one more worth mentioning is Aldec. They provide the HES platform hardware emulation system. HES is interesting because it's often positioned as a hybrid solution, capable of supporting both emulation-style use models and traditional prototyping. They also have a large library of pre-verified interface components called transactors, and they've been a pioneer in cloud-based prototyping, offering their HES DVM partitioning software accessible via AWS.
Cloud-based prototyping, that sounds like a significant shift. So it seems like the software is really the secret sauce that makes all this incredibly complex hardware actually usable and work together effectively.
That's a great way to put it. The software is absolutely critical. The partitioning and synthesis tools, like Protocompiler or the tools from Cadence and Siemens, are really the brains of the operation, automating that incredibly complex ASIC to FPGA conversion. Then, of course, you have the FPGA vendors' own tools like Vivado from AMD Xilinx or Quartus from Intel, which handle the final, detailed physical place and route step within each FPGA chip. And then there's debug. And then there's a whole diverse suite of debug tools. It ranges from the basic on-chip logic analyzers provided by the FPGA vendors themselves, things like AMD's ILA, Integrated Logic Analyzer, or Intel's SignalTap, all the way up to highly advanced third-party solutions designed specifically for deep prototype debug. And the integrated debuggers built into those commercial platforms, from Synopsys, Cadence, and Siemens, all working together to try and gain that vital visibility into what the prototype is actually doing.
Okay, you mentioned FPGA hell earlier, and it sounds like the debug phase is where designers really encounter it. What exactly is this notorious hell, and how are teams finding ways to navigate out of it?
Yeah, FPGA hell is the, let's say, colorful term that vividly describes the often agonizingly slow and difficult debug cycles historically associated with FPGA prototyping. The absolute core problem is the fundamental lack of visibility into the internal state of the running FPGA. It's nothing like simulation where you can basically see any signal you want anytime.
Right. In simulation, it's all just data.
Exactly. But in a physical FPGA, to observe an internal signal, an engineer traditionally has to explicitly probe it. That means adding dedicated debug logic into the design instrumenting it. And that requires going through a full resynthesis and place and route cycle for the entire design, or at least for the affected FPGAs in a multi-FPGA system.
And how long does that take?
For a large, complex source spread across multiple big FPGAs. That recompile cycle can easily take 8 hours, 12 hours, sometimes even 18 hours or more.
A whole day or longer just to add a probe?
Potentially, yes.
Yeah.
So imagine you have a bug, you make an educated guess about where to look, you add probes, you wait 12 hours, only to find out your probes weren't quite in the right spot or didn't capture the event.
Ugh. Back to square one, lose another day.
Exactly. It's like trying to find a needle in a haystack, blindfolded, and the haystack literally regrows every time you touch it. That incredibly slow, iterative loop of guess, compile, test, guess again. That is the very essence of FPGA hell.
So if your first guess, your first hypothesis about the bug, isn't right, you've essentially just burned an entire day, maybe more, of critical project time. That sounds incredibly frustrating and expensive.
It absolutely is. And the traditional on-chip logic analyzers we mentioned, like ILA and SignalTap, they have limitations too. They're typically limited in the number of signals you can probe simultaneously, maybe around 1,000, like a 1024 is common. And maybe more importantly, they're limited in their trace depth.
Meaning how much data they can capture.
Right. They usually only capture a few thousand clock cycles worth of data around a trigger event. That's often just not enough context to understand complex bugs in a big SAW, especially issues that develop over longer periods.
Yep.
Plus, the probe logic itself consumes valuable FPGA logic resources and can sometimes even affect timing.
Okay, so that's the hell. How are the advanced solutions finally tackling this age-old visibility problem? What's changing?
Well, thankfully, a new generation of tools and techniques is fundamentally changing the game here. We're seeing real progress. One approach is instrumentation-based solutions. Think of tools like Tektronix's Certus. These systems allow you to instrument or prepare for probing tens of thousands of signals up front, but with much lower resource overhead compared to traditional methods.
Tens of thousands. That's a huge jump.
It is. It dramatically increases the visibility you can get within a single compile cycle. You instrument broadly once, then select which subset of those signals to actively monitor during runtime. Then there's another category, external storage-based solutions. Companies like Exhaustive offer systems that use the FPGA's high-speed transceivers to stream vast quantities of trace data off-chip in real time to external memory or storage.
So you're not limited by the on-chip memory depth.
Exactly. This allows for incredibly deep traces, potentially billions of clock cycles, giving you a much longer history leading up to a bug. And a really critical breakthrough here is how the major commercial prototyping platforms, the APS, Protium, Veloci systems, have deeply integrated these kinds of advanced debug capabilities. They now offer things like seamless visibility across all the FPGAs in a multi-FPGA system, deep trace capture, and crucially, they often correlate the captured waveform data directly back to your original RTL source code.
So you're not just looking at raw signals, you see it in the context of your design code.
Right. And some even correlate it with software execution traces from the processor. They're systematically working to bring that emulation-like deep visibility into the high-speed prototyping environment. It's a direct assault on the traditional pains of FPGA hell.
Okay, that covers getting visibility into the hardware side. But how does software itself play a role in actually finding these bugs on the hardware prototype?
That's a great question, because a prototype is rarely just a standalone island running hardware tests. It's almost always connected to a host PC, typically via a high-speed interface like PCIe.
Right, for control and data.
Exactly.
Yeah.
And this connection enables powerful techniques like software-driven testing, sometimes called co-emulation or co-verification. You can have a sophisticated test bench program running on the host PC. This test bench generates high-level stimulus, maybe simulating network traffic or user interactions. This stimulus is then translated by special software components called transactors. These transactors bridge the abstraction gap, converting the high-level commands into the precise, cycle-accurate signals needed to drive the interfaces of the design running on the prototype.
So you can reuse your simulation test environment.
Precisely. It allows design teams to leverage their existing, often very complex simulation test benches and run them against the much faster prototype hardware. This enables extensive, automated regression testing that would be impossible in pure simulation. And when it comes to the actual debug process, a systematic approach is absolutely paramount. You have to be methodical. It should usually be incremental. First, just verify the physical board itself is okay. Then check the clock and reset networks are stable. Then bring up individual IP blocks one by one, and only then try to run the full SOCI.
Makes sense. Don't try to boil the ocean.
Exactly. And when a bug does surface, it's frequently really ambiguous at first. Is it a hardware bug? Is it a software bug in the driver? Or is it some complex interaction between the two?
The dreaded hardware-software integration bugs.
Those are the killers. Modern platforms are really focusing on enabling unified debug environments to tackle this. Environments where the software developers can use their familiar tools, like JTAG debuggers, to step through code running on the prototype's processor. While simultaneously, the hardware engineers can be looking at RTL-correlated waveforms captured from the FPGA logic, all-time synchronized. This allows for true collaborative diagnosis of those complex cross-domain bugs.
That collaborative aspect sounds incredibly important for cracking those tough problems. Okay, this deep dive has really painted a clear picture of how far FPGA prototyping has evolved. It's gone from this maybe niche, difficult task to an absolutely indispensable pillar of modern chip development. Looking ahead now, what does the future hold? Where is this critical technology going next?
Yeah, it's a field in constant dynamic evolution. It has to be, really, driven by that relentless increase in source complexity and also by the emergence of powerful new technologies. The traditional idea of a standalone prototype is definitely giving way to a new paradigm, one that's characterized by much deeper integration with other tools, much more flexibility through the cloud, and increasingly the influence of artificial intelligence. Arguably, the most significant immediate trend we're seeing is the convergence, that tight integration of hardware emulation and FPGA prototyping into hybrid systems.
We touched on that with the Cadence example.
Exactly. Historically, they were often very separate domains, maybe different teams, different tools, different flows. It created this kind of wall between the two verification phases. Now, platforms like Cadence's Palladium Protium Dynamic Duo or Synopsys' ZeBu HAPS Continuum are built around shared infrastructure, common compilers, common debug environments.
So the idea is you can leverage the deep hardware debug strengths of the emulator.
Right. Find those really tricky hardware bugs there.
And then seamlessly, quickly migrate that same design representation over to the faster prototype for extensive software validation and system testing.
Precisely. It allows design teams to truly get the best of both worlds without the massive overhead and friction of maintaining two completely disparate, incompatible flows. And the lines are blurring even further. We're seeing prototyping platforms gaining more and more of those emulation-like deep debug features we discussed. There are even concepts for hybrid systems where parts of a design might run on an emulator, maybe the processor subsystem for high visibility, while other parts run simultaneously on a prototype, like high-speed interfaces connected to real devices.
Wow, that's really integrated.
It's a direct strategic response from the EDA vendors to tackle that decades-old fundamental trade-off between verification speed and debug visibility.
Okay, convergence is big.
Right.
What about the cloud? You mentioned Alldec doing cloud-based partitioning. How does cloud infrastructure change the game more broadly for prototyping?
The migration of prototyping resources, both the complex software tools and potentially access to the hardware platforms themselves to the cloud, fundamentally alters the economics and accessibility. Traditionally, getting into serious FPGA prototyping required significant upfront capital expenditure, buying multi-million-dollar systems, setting up labs.
Right, a big barrier to entry.
A huge barrier. Cloud-based models shift this towards a more flexible operational expenditure, UpEx model. You pay for what you use when you use it. This really democratizes access to state-of-the-art verification technology. It allows smaller companies, startups, or research groups to potentially leverage the same kind of powerful tools previously only available to large corporations.
And for the big players.
For large enterprises, it offers unprecedented elasticity and scalability. Imagine being able to spin up, say, hundreds of virtual prototype instances in the cloud to run massive parallel regression test suites overnight, covering huge parts of the state space, and then just spin them all down in the morning when the tests are done.
That sounds incredibly powerful for verification throughput.
It's potentially transformative. It could enable true continuous integration, continuous deployment CI/CD pipelines, but for hardware verification, constantly testing changes against a massive bank of virtual prototypes.
CI/CD for hardware. That's a fascinating concept. Okay, last area, AI and machine learning. We hear about it everywhere. How might AI impact this field of FPGA prototyping?
It's definitely coming, and in fact, it's already starting. The semiconductor industry is now actively applying AI and ML techniques to improve its own design and verification processes. It's creating this powerful self-reinforcing feedback loop.
Using AI to design the chips that will run AI.
Kind of, yeah. Two key areas are rapidly emerging specifically for prototyping. First is AI-powered partitioning. That multi-FPGA partitioning problem we talked about with its huge search space, complex constraints, timing trade-offs, it's an almost ideal candidate for machine learning.
How'd that work?
Future partitioning tools could use trained ML models. These models would learn from the results of thousands, maybe millions of previous partitioning runs on different designs. They could then use that learned knowledge to more intelligently predict routing congestion, estimate timing impacts of different cuts, and ultimately produce higher quality partitions much more quickly and effectively than purely algorithmic approaches. Siemens has publicly discussed leveraging AI for mapping complex designs onto these huge new FPGAs, like the Versal Premium.
So smarter, faster partitioning. What's the second area?
AI-powered debug. Debugging at its core is often about finding that elusive needle in a haystack within massive, complex data sets, simulation logs, waveform traces, error reports.
And machine learning is good at pattern finding and big data.
Exactly. Machine learning excels at this. You can envision AI tools that analyze gigabytes of trace data, automatically classify bug types, trace signal causality backward from an error, and intelligently guide engineers much more directly toward the root cause of problems. This could significantly reduce the laborious manual effort involved in sifting through data. This application of AI in debug is still relatively early, but its potential to dramatically improve debug efficiency is just enormous.
What an insightful journey that was, really charting the evolution of FPGA prototyping. It's so clear how it's shifted from being, this highly specialized, maybe even painful task into something absolutely indispensable for modern chip development.
It really has. And I think the most critical shift, the one that's had the biggest impact, is its move from being just a pure hardware verification tool to becoming a comprehensive system-level validation platform, especially its role in enabling that parallel software development, that shift left. That's been the primary force in compressing those incredibly demanding product development cycles and, frankly, mitigating the immense financial risks involved in making these chips.
So when you boil it all down, what does this mean for you, our listener? Well, it means that the next time you pick up your smartphone or use any device powered by a truly cutting-edge chip, you can appreciate the incredibly intricate layers of verification, like FPGA prototyping, that went into making sure it actually works reliably and performs as expected. And the ongoing innovations we've talked about, these ever larger, more capable FPGAs, the deeply integrated platforms from the EDA vendors, and especially that convergence with emulation and the dawn of AI assistance, they are systematically solving verification problems that honestly seemed almost intractable just a handful of years ago.
It's true. And this progress itself raises a really profound, maybe even slightly meta question for the future. As these AI tools become increasingly sophisticated, not just in debug, but potentially in partitioning, maybe even aspects of design itself, how might this accelerate the very pace of technological innovation? What new challenges and what incredible new opportunities will emerge when the very tools we use to design the future are themselves built on increasingly intelligent learning systems?
That is definitely something compelling to consider as we move deeper into this ever more interconnected and, well, intelligent world. And that concludes our deep dive into the fascinating world of FPGA prototyping for ASIC verification. We really hope you've gained some compelling insights and feel much better informed about this critical foundational aspect of modern technology. Join us next time for another deep dive into the world's most compelling information.